This is what connected.
Oh, that's only the code.
Time travel. We're back in where we were years ago. Are they all which is I see. So it was extremely hard to prepare this talk because the last part of my brain was turned off. Well, it's good. That's nice to be back.
So if you want color, then okay, great.
Staple.
Good staple.
That's super helpful. Oh, now you've seen the talk, so you don't need to come.
There are words that you also say strategies in these slides.
Are you as excited to be here as we are to see you?
I'm a lot more nervous than you are.
I don't know, being an audience member and talking can be quite nerve-wracking.
You'll see, I have some questions for you. I have 25 after. Oh, I lectured to 600 people. Well, if you need to have a signal, you know, I could be giving my talk.
Is this a costume or are you using water?
So,
Those are ranges.
when people teach, you know,
You're which costume? There were three witches at your party. I was almost a witch too.
I think you'd be called a warlock.
They didn't have warlock hats.
Not the same.
Good afternoon, everyone. And welcome to the Coxeter Lecture associated to the major thematic program in calculator theory, geometry, and dynamics. We're absolutely delighted to have Professor McMullen here, no stranger to the Fields Institute, a central name in this whole subject. Maybe I'd like to just to say, for those who might not have been at a Coxeter lectureship before, just to say that this lectureship is named after Professor Coxeter, a famous figure in geometry, perhaps very far ahead of his time in a number of developments which led to new discoveries in geometric group theory, apart from his work on the structure of symmetry in high-dimensional space. So it's a great honor, I think, for us to remember that legacy here at the University of Toronto, where he was professor for most of his long career, well into his 90s. I think I last heard a lecture from Professor Coxeter at the age of 94 or thereabouts. Other school here. So now, just to say a word about the Coxeter lectureship series. It's a series of 3 lectures, common theme, and of course our guest here is Professor McMullen. This is an extra feature of in the midst of a very rich program which is going on right now, which is lasting the whole 6 months program in calculator theory, which has, I'd just like to boast about the elements of these thematic programs, because it's this mixture. There are postdocs here for the whole period of time. There's a graduate course going on given by the Dean's Distinguished Visiting Professor, Laden Bestima. There are seminars, short-term visitors, long-term visitors, workshops. It's actually an incredible display of mathematical activity and organized around this common theme. Very much within the theme of the major thematic program are the lectures, Coxeter lectures. Professor McMullen, welcome, and thank you for coming.
Thank you. Well, I'm not sure what to add to that, but it's a real pleasure to be back in Toronto, and especially to give some talks in honor of Coxeter, who has played an important role in my own mathematical life. I have to admit, I did not learn what a Coxeter group was until roughly 15 years after my PhD. but they're great. And I've written several papers that involve them now, and they just are increasingly central, even in the field I'm about to talk about today. This is a fantastic program that's going on now, so I'm very glad to be able to meet the people here who are participating in it. And this is also a nice occasion to remember my esteemed Mary Edwards colleague. Okay, so let me start this series. I want to give a very general talk today. I should say most of the talks should be pretty accessible. You don't really need to have been to one to attend the next. But this will be the broadest. So I want to talk about the geometry of totally geodesic planes. So just like a flat copy of R2, say sitting in space, but what I really want to discuss are what I call planes in confinement. So you have this infinite extended object, but you force it to live in a bounded realm. So one way to imagine this is you take a random plane in R3, and then you take the quotient of R3 by the integer lattice. And you get a 3 torus. And then this huge plane maps down to something that wraps around in a very complicated way in the 3 torus. And studying the way planes are deployed when they're forced to live in these small worlds is a very rich subject. So I'm going to describe 3 examples of the behavior of these totally geodesic planes, some of which we understand, some of which we don't. So the 3 examples are going to be Euclidean planes first, but they're not going to be in 3 space or a torus. They're going to map into the space of lattices in R3. The second example will be about not flat planes, but negatively curved hyperbolic planes, and these will be immersed in a hyperbolic 3-manifold. And then the third example will be hyperbolic planes immersed in moduli space. This is the one that's most closely connected to the program of this semester. And I hope to display some of the interesting interactions and differences and similarities between these 3 regimes. So let me start, though, by talking about the real numbers with 1 dimension. So I'm going to let 2 lines around x denote the distance from x to the integer. So it's like the fractional part of x. Here's a couple of questions for the audience. They're true or false. So the first question is it true that if you take the multiples of f, so here n ranges over the integers, that the infimum of the fractional part is equal to 0? That is, if I give you a number x, can you find a multiple which is as close to the integers as you like? True. Okay, well let's make it a little harder then. Let's ask if you can make the product of the distance from the integers and n to be equal to 0. So I not only want to be able to get the multiple close to the integers, but I want to be able to do it within a certain amount of time. So I want to be able to get within distance 1 over n infinitely often. And this turns out to be false. And if you take something like the square root of 2, you can't quite get this to happen. As far as anyone knows, if you take the cube root of 2, it works. No one will probably ever prove it. My personal opinion. Well, we're going to try to find a statement that interpolates between these 2. And it's the following. Suppose we take 2 real numbers, and we try to make this statement true by combining it with this statement. So we take n times norm of nx, and then we multiply it by n times y, the fractional part of n times y, for some other number y. Now, for example, if y were equal to x, this would be n times nx squared, and in fact, this would be equal to 0. So what's the answer to, see this quantity here, this turns out to be bounded infinitely often. So all you have to do is get something in there to push it down to 0. And this thing is 0. So that should work, right? You just have to get in sync. Well, this is unknown. This is what's called Littlewood's conjecture. It comes from the 1930s. And what I'd like to describe is how this is related to number theory and to planes in the space of lattices in R3. So a lattice in R3 you should just think of as a discrete periodic set that's isomorphic to Z3. But what I'm going to be interested in is not the ordinary distance function on R3. I measure the distance of a point from the origin in this bizarre way. I take the product of the three coordinates. Sorry, that's what I'm doing today. This is the unit ball for me. It's a sort of a non-compact star. It's definitely not convex. So those are all the points within, say distance 1 of the origin. The ordinary ball is preserved by the orthogonal group. This kind of norm is preserved by a different group of linear transformations, namely the diagonal matrices of determinant 1. If you scale A1, x1, x2, and x3 by just different factors whose product is 1, this norm remains the same. So this is now sort of our isometry group for this new kind of geometry. So this group of diagonal matrices is in fact a plane. It's isomorphic to R2. If you like, the entries of this diagonal matrix can be written as e to the t1, e to the t2, e to the t3. So they're specified by 3 real numbers. And those numbers need to have the property that their sum is 0. So that turns it into a 2. Okay, now here's something an interesting thing we can try to do. Let's try to figure out something like how well packed this lattice is. So let's look for the shortest vector in a given lattice. So we look at the non-zero elements in the lattice, and we look at what the smallest norm is in the non-zero elements. Now, because of the fact that this ball is non-compact, you actually have to examine an infinite region in space to see if there's a lattice point within this ball. It's not nearly so simple as the case of a compact ball. And in fact, here's a tricky problem. Can you find even one lattice that doesn't have lattice vectors that are arbitrarily close to 0? Can we find a lattice where we can guarantee that there's no point where the product of the triple of coordinates is close to 0? Well, number theorists immediately will say yes, because that n stands for norm. And if you take a totally real cubic field, then embed it into R3 by taking a point in the ring of integers to that number, its Galois conjugate and its other Galois conjugate, or use the 3 different embeddings of this real cubic field into R. That forms a lattice, and the norm of all of these elements is just the ordinary norm in the number field, which is an integer. So n of L is equal to 1. Well, here's the first open problem I want to mention. It's called the Margulis conjecture. It says every lattice in R3 with the property that the norm is positive comes from a cubic number field by this kind of construction. Now, what does this have to do with planes? Well, remember we have this action of the diagonal group on this lattice. That's an isometric action for the norm in question. So if L has the property that its norm is bounded below, then so does any other lattice in the orbit of L under the action of A. So this is a picture of the space of lattices of the orbit of the lattice I just mentioned under the diagonal group. And what happens is that it wraps up and forms a compact torus. And the reason for that is that there's a group of units in the field, and those units give you a lattice inside of this diagonal group A. So to say that here's an equivalent formulation of the Margulis conjecture. If you have a plane, which is the orbit of a lattice, under the action of the diagonal group, and if that plane is bounded in the space of lattices, the space of lattices is non-compact, because you can have lattices that have very short vectors in them. But if this plane is magically bounded, then in fact, the plane has wrapped up and formed a compact torus, which is sort of a miracle for it to wrap up and form this compact torus. And what this is saying is that the only source of miracles in mathematics is number theory. Okay, and as I said, this is then the stabilizer of this lattice is the group of units in that integers. Now this conjecture, which is about planes, actually implies Littlewood's conjecture. So in fact, if you had a counterexample to Littlewood's conjecture, it would be specified by a pair of real numbers, x and y, and you just form this lattice, spanned by the two obvious basis vectors, and then the third one with x and y thrown in. And then a typical element in this lattice is of the form some integer plus nx, some integer plus ny, and then the integer n. And the norm of this is at least the fractional part of x times the fractional part of y times n. So the assertion that this inf is positive is the assertion that this quantity is greater than 0. So it would give a bounded torus. And Margulis would say that bounded torus has to come from a number field, but this lattice clearly doesn't come from a number field. And so that proves Littlewood's conjecture. That's the idea. Okay. So what's known? Well, there's a big theorem, which was proved by Einsiedler, Katak, and Lindenstrauss, which is that if you have a bounded plane in the space of lattices, then the Hausdorff dimension of its closure is 2. So remember, this object is already two-dimensional. And I'm trying to prove that it's a torus. And what I can prove is that its closure is two-dimensional. It's pretty close, right? How can its closure not just be a torus then? Well, it might be locally like a Cantor set cross a plane, and that Cantor set would have to be then of Hausdorff dimension 0. So it could look like a very thin set cross a plane. That's potentially allowed. But this is a huge progress on the conjecture, and as a corollary is that the set of counterexamples to the Littlewood conjecture itself has Hausdorff dimension 0. So you're unlikely to find it by a computer search. Okay. Personally, I love this result, but it doesn't give me confidence that the Littlewood conjecture is true. And the reason is that if we go to down a dimension, and we look for geodesics on a Riemann surface as an analog of planes in the space of lattices, it's known that if you take the closure of a simple geodesic on a hyperbolic surface, that's a closure of a sort of a one-dimensional plane, and the result has Hausdorff dimension 1. And in fact, it does not have to be a closed geodesic, and it can have this transverse Cantor set of Hausdorff dimension 0. That was proved by early in the series. So what this, in some sense, one way to interpret this statement is that if there is a counterexample to Littlewood's conjecture, it has to be some sort of laminar object, like this. And I would love to make that more precise. And I should say that's not a very strong argument that this conjecture should be false. It just highlights what the remaining difficulty is. Okay, let me just before I leave lattices, let me just tell you a little bit about my own interest in lattices. When you have a lattice, there's something called its covering radius, which is sort of how big you need to make balls around the points to cover Rn. Except these are norm balls rather than the usual Euclidean balls. And there's a conjecture through Minkowski that says if the volume of Rn mod L is 1, then the covering radius is less than the covering radius for the obvious lattice En, which can be computed exactly as 2 to the minus n. So my interest in lattices has to do with this conjecture. And the thing to notice about this conjecture is like the Margulis conjecture, if we apply a diagonal matrix to L of determinant 1, it doesn't change its covering radius. This conjecture was proved in a series of increasingly difficult papers for n equals 2, 3, 4, and 5, up to, starting with Minkowski and going up to Escobedo in the 1970s. Let me explain a little bit about what's been done on it recently. Within the space of all lattices, there's something called the well-rounded lattices. These are the ones where the shortest vectors in the lattice span Rn. So there have to be lots of ties for the shortest vectors. An example, for example, is the E8 lattice. It's sitting in an 8-dimensional space. It has 240 short vectors. This cubic lattice has plenty of short vectors that are timed, and certainly enough to span R3. The nice thing about the well-rounded lattices is they're compact in the space of all lattices. In fact, they form a spine. You can retract the space of all lattices to the well-rounded ones. And my work on this was centered around the following result, which is a sort of recurrence theorem. It says that if you have a lattice whose orbit under the diagonal group is bounded, then its closure contains a well-rounded lattice. This is a kind of recurrence result, and it's potentially a step in the proof of Margulis's conjecture, but this also is sort of half of the traditional proof of Minkowski's conjecture that's been carried out in these other dimensions. And other people have done the other half in more dimensions, so we now know, putting them together, that Minkowski's conjecture holds for n less than 10. Okay, on to part 2. So I now want to discuss the behavior of planes in hyperbolic 3 manifolds. And these will be hyperbolic planes, not the usual Euclidean plane. You can think of them as being modeled on the unit disk or on the upper half plane in the complex numbers. And what I'm interested in is a map of such a hyperbolic plane into a 3 manifold. A 3 manifold is just the quotient of the hyperbolic ball by the action of a discrete group of isometries. And I call its image a plane inside of M. Totally geodesic. And here we have another beautiful example of a dichotomy for the behavior of planes in confinement. And this is now a theorem, whereas Margulis's statement was a conjecture. Now, this is the kind of theorem that inspired Margulis's conjecture. So the theorem, which is due to Ratner and Shaw, is that if you put a plane inside a compact 3 manifold, then either it's dense in the 3 manifold, which is what will happen if you're not extremely lucky, or the image is a closed surface immersed in the manifold, compact surface. And that is a miracle. Okay, now why is that a miracle? Well, forget about planes. Suppose I map a line isometrically into the hyperbolic 3 manifolds. In other words, suppose I look at a geodesic in this hyperbolic 3 manifold. The geodesic is also almost always dense. But if I'm going to have a closed surface, then there have to be plenty of geodesics in this plane which map to closed geodesics, because this closed surface has lots of closed geodesics. And that's already sort of a miracle, that the plane should pass through a closed geodesic just once. But think about what has to happen. This closed surface is completely filled by a mesh of closed geodesics in every direction. And so this plane has to magically contain not just one closed geodesic, which is easy to arrange, but closed geodesics in, for example, a dense set of directions, which is like infinitely many conditions. So it should never occur, which means this theorem should be easy to prove. But it's not, because this actually does occur. Okay, so here, this is the picture schematic. That's my idea of a 3 manifold. This is a compact surface inside of it. That's the miracle. And the typical example, I didn't draw, but it would be dense. Okay, so I'd like to show you actual examples of these guys, because hyperbolic 3 manifolds are very concrete objects. The reason they're concrete is that we can think of the universal cover as just the unit 3 ball. And the boundary of that we can think of as the Riemann sphere. And it turns out that the fundamental group here, gamma, just acts by Mobius transformations on the Riemann sphere. It acts by the usual conformal automorphisms of the sphere that we know from complex analysis, and that you prove as an undergraduate preserves circles. Now, circles on the sphere have a meaning in 3-dimensional hyperbolic geometry. They are the boundary of hyperbolic planes. So this is maybe the only picture I need to draw, or should draw. So when you see a circle in the plane, if you're a hyperbolic geometer, you think of that as just the trace at infinity of a hemisphere which is orthogonal to the plane. And this hemisphere is a totally geodesic two-plane inside of H3. So if I want to describe a plane inside of a three-manifold, instead of doing that, I can pass to the universal cover and describe a collection of planes that's invariant under this group gamma. And it's hard to draw those planes in hyperbolic 3 space, but I can certainly draw the corresponding circles on the sphere. Okay, so a plane in a three-manifold corresponds to an invariant collection of circles on the sphere. So here's an example of a picture of a plane in a compact three-manifold. Beautiful, huh? So these are, look at all those circles. Let me show you another plane in the same three-manifold. Okay, so the question is, what is the difference between these two pictures? I mean, obviously this one looks more ordered and so on, but just in terms of the circles that you're seeing, there's a property of the circles in this picture which distinguishes it from the collection of circles in this picture. What makes this one look so much more hairy and this one not? Any thoughts? Yes? Louder?
It seems like in the first picture, there's a lower bound on the sizes of the cells, and that one took the
Okay. Okay, other thoughts?
Every intersection point has more than two circles.
Yeah, there is a lot of miracles going on in this network, but what's going on here? Yeah, Matt?
That plane has no stabilizer in that group.
I'm asking you a question about this hairy picture. Forget about the group. What makes this picture look hairy and this one not?
Like this.
What?
Intersection points.
So, there's a major difference.
The bigger circles.
Thank you. So in this picture, the diameters of the circles go to 0. There's only finitely many circles whose diameter is bigger than a given epsilon. In this picture, there are infinitely many large circles. I mean, of course, there's only finitely many in each picture, but there's a lot more big circles in this picture. And that dichotomy corresponds exactly to whether or not the plane in question gives you a closed surface in the three-manifold or gives you a dense surface in the three-manifold. In fact, here, the collections of circles you see will be dense in the space of circles, and here the collection of circles you see will be a closed discrete subset of the space of circles. Okay, so this picture, the very ordered picture, corresponds to the closed surface, and this disordered picture corresponds to the dense surface in the quotient field. Okay, now, what about examples, though, of these miracles? Well, they do exist, and I already showed you one of them. Let me just show you a few more. So this is the orbit of a circle under some group of Mobius transformations. In this case, it's the group SL2Z adjoint I. That happens to give a finite volume quotient, not quite a compact quotient. But that represents another totally geodesic closed surface. Here's another totally geodesic closed surface. Here's another one. All of these patterns that I'm showing you come from arithmetic. They come from things like SL2Z adjoint I. Well, not quite. Some of the patterns come from Coxeter groups. So in fact, to draw these pictures, I looked in the back of Rita McLaughlin's book on arithmetic hyperbolic three-manifolds, and they list all of the tetrahedra that give discrete reflection groups in H3. Some of them are arithmetic, some of them are not. What's the language for discussing these? Coxeter diagrams. There's just a beautiful list of Coxeter diagrams, and I programmed them all up, and I made a mess of pictures. So the fact that there's one beautiful picture like this just means the corresponding three-manifold has one closed surface inside of it. But these arithmetic ones have a much stronger property. To each one of those arithmetic groups, there's associated infinitely many circle patterns. That is, there's infinitely many closed surfaces inside of them. And an open problem is to show if you do have infinitely many miracles, did the manifold itself have to be arithmetic invariant? Okay, so the final topic I'd like to address in this setting, namely the study of hyperbolic three manifolds and planes within them, is a generalization of this rigidity theory to three manifolds with boundary. So if you like, you might say, well, we're going to think about infinite volume three manifolds. We're not going to require that gamma is co-compact or a lattice. Or you might just say we want to consider hyperbolic manifolds maybe with totally geodesic boundary. So here's a picture of what the three manifold looked like. Its boundary is a Riemann surface of higher genus, itself with a hyperbolic structure. This can be thought of as the convex core of a complete hyperbolic three manifold of infinite volume. In any case, where do these pictures come up? They are part of the study of, they arise in the study of knotted handle bodies in R3 in much the same way as finite volume three manifolds arise from the study of ordinary knots in R3. So sufficiently complicated knotted handle bodies, that is thickened surfaces of genus 2, for example, sufficiently complicated knotted handle bodies have the property that their complement is a hyperbolic three manifold with boundary, and this genus 2 surface is, of course, this boundary that's being shown here for the three manifold. What do these objects look like when we really look at them geometrically? We go back up to the universal cover and draw the surfaces. Well, the boundary components of the manifold lift to give hyperbolic planes that cut off a piece of hyperbolic space where there's no action going on in terms of the fundamental group. So we pass from a setting where we have dense sets of circles on the sphere to where we have a family of disjoint circles on the sphere, one corresponding to each boundary component. And it turns out that this configuration of circles has the special property that no two of the circles touch each other. So the complement of this union of circles, which is called the limit set, the part shown in black here, is a topological object called a Sierpinski carpet, or Sierpinski gasket, or Sierpinski curve. It's a sort of one-dimensional analog of the Cantor set. So in fact, if you take any collection of circles on the sphere with the property that no two touch and the property that they're dense, the complement of that collection is homeomorphic to what you get for any other collection. So the topology of this thing is the same, no matter which three manifold or geodesic boundary I focus my attention on. So in this setting, working with Mohammadi and Hio, in 2015, we extended Ratner's theorem to show that any plane in the convex core of this manifold is again either dense or covers a closed surface. And this was, I think, the first example of an extension of Ratner's theorem of this type to an infinite volume manifold. But there's a defect from the point of view of three-dimensional hyperbolic geometries, which is that the previous manifolds obey Mossbauer rigidity because they're closed. This manifold is not rigid. It should be thought of as one very special representative of a bunch of different hyperbolic structures on the same topological space. And what happens when you start deforming this manifold is that these circles become fractal quasi-circles. And we use the fact that they're round circles very much in our original proof. What happens when they become fractal quasi-circles? So what happens is the boundary then is no longer geodesic. Well, the first thing I want to say is no one had ever seen a picture of what happens when we deform these manifolds. So this is the first image, to my knowledge, that was ever drawn of an actual, a typical hyperbolic three manifold with acylindrical type, and that means it can be deformed to something with round circles here. And you see every one of these round circles has become some sort of quite complicated fractal object. In fact, it has dimension 1, but they still don't touch. This figure is homeomorphic to the preceding figure. And after about 2 years of work, we were able to show rigidity holds in this setting as well. And the main statement in the proof is actually a theorem that has nothing to do with Kleinian groups. There's some sort of recurrence that's required in all proofs in homogeneous dynamics in this style of argument, and that boils down to a statement that can be made as follows: thick carpets have thick slices. So what that means is if you think of this, I'm not sure this is really a carpet, it looks like it's very moth-eaten, but think of this black stuff as some sort of lacework. If you cut it with a round circle, you see a subset of that circle that contains a thick Cantor set. And that's the key to this proof. And by the way, there had to be a huge psychological leap made here, which was, it's not true that this circle meets the locus in a thick Cantor set. That's not the statement you need. You need that it contains a thick Cantor set, and that's what it turns out to be true quite generally. And I want to mention that this image was produced by McMullen in 2008. Okay. Topic 3. So we're now coming to the main topic at the Fields Institute, and this is the topic that my remaining 2 lectures will elaborate. It has to do with the study of planes in the moduli space of Riemann surfaces of a fixed genus G, say G2 or more. Okay, so MG is a space that has one point for each isomorphism type of closed Riemann surface of genus G. It turns out that Riemann surfaces of genus G depend on 3G minus 3 complex parameters for G bigger than 1. So this is, in fact, a complex variety of dimension 3G minus 3. A lot is known about it. It's irreducible, it's not compact, etc. It has many similarities to the quotient of a homogeneous space by the action of a lattice, but it's not the quotient of a homogeneous space by the action of a lattice. So what we're going to try to do is understand the previous 2 theorems, and in particular this radar rigidity phenomenon, and the fact that planes are either very badly behaved or very well behaved, in the setting where the target is no longer a homogeneous space, but it's something of equal or greater interest, namely this moduli space that's fundamental in the classification of algebraic curves. Okay, so the first thing I have to tell you is what is a complex geodesic. That is, I'm going to be interested in maps of the hyperbolic 2 plane into MG. Previously, I just asked that this map was totally geodesic. There is a metric here, the Kobayashi metric, with respect to which this map will be totally geodesic. But equally important, both spaces have a complex structure, and I want to require that this map is holomorphic. So I add that condition to the local isometry condition, and we get what's called a complex geodesic mapped into MG. So to elaborate the statement I just hinted at, on moduli space, there's a natural metric called the Kobayashi metric or the Typhoon metric. They turn out to coincide for this manifold. And a complex geodesic is a holomorphic isometry from the upper half plane into MG. I should say local isometry because it might come around and meet itself. Now, there's lots of complex geodesics. In fact, if you give me a point in moduli space and you pick a tangent direction, there is a complex geodesic passing through that point in the given direction. That's already kind of amazing that this space, which is rather inhomogeneous, has tons of isometrically immersed copies of these planes. There's lots of planes of constant negative curvature sitting inside, immersed in moduli space. So one can ask, if I have one of these planes in confinement, if I have such an immersed plane, how does it behave? And of course, your conjecture would be that its closure is dense, unless a miracle occurs. Now, how do you say what should happen when a miracle does occur? Well, one of the things that you might think could happen is that this plane's closure is one of these fractal objects, the kind that enter potentially in the Margulis conjecture. Maybe its closure is something that's a Cantor set across a manifold locally, or something even worse than that. So the first sign that something extremely good is going on would be that the closure is always a reasonable space. And in fact, this is a beautiful theorem. The closure of the image of a complex geodesic is always an algebraic subproperty of modulices. This theorem was proved by me in the case of genus 2, and then the much deeper case of general genus was carried out by Alex Eska and Mary Mirzakhani and Amir Mohammadi, with the final touch put on it by Simeon Philly. So this result is, again, a sort of Ratner-like dichotomy or rigidity theorem for planes in confinement in modulices. Okay, now, do these miracles occur where the closure is not the whole moduli space? Well, there's an extreme example of such a miracle. The extreme example is that you don't have to take the closure of the plane. The plane, once again, maps to a two-dimensional surface in moduli space. It's just giving the universal cover of an embedded or immersed hyperbolic surface in the triangle. So, in general, when we have a map of the hyperbolic plane into moduli space, we can take the stabilizer of the map and it factors through the quotient of the hyperbolic plane by that stabilizer. We'll call this quotient Riemann surface V. If gamma is a lattice, then this quotient curve V, or rather its image in moduli space, is an algebraic, isometrically immersed curve, and such objects are called hyperbolic. So this is a very extreme example of a miracle, and it's similar to the miracle of having a compact surface in a hyperbolic three-dimensional. So to bring this down to Earth, let me give you an example of a complex geodesic in moduli space of curves of genus 3. And I think one of the great appeals of this subject is that, in fact, the examples are much easier than what you usually learn about in graduate school. So, for example, in graduate school, this object is treated as essentially untouchable. You can prove theorems about it, but you can never see it. It's some, formal mystery. This math F is some sort of exotic transcendental thing that has no formula. And certainly the image in M3 is some curve and something you can't understand anyway. But in fact, these complex geodesics are very elementary to describe, and they can be described in the following way. So what I'd like to do is first construct for you a surface of genus 3. So this will be one point in the moduli space of curves of genus 3. And what I'd like to do is take the regular seven-gon and identify opposite sides. But the problem is it doesn't have opposite sides. So I put another copy of it below, and now the 7-gon magically becomes a 12-gon because these two edges have disappeared. And now I do have opposite sides. So I'm going to glue this edge here to this edge here, this edge here to this edge here. And the result is a very symmetric Riemann surface of genus 3. So I've now described a point in the moduli space of Riemann surfaces of genus 3. This point, of course, has a lot of special symmetry. It has an evident automorphism on one side. Okay, so that's one point. How about getting a whole hyperbolic plane's worth of points? So what I do is I think of the first heptagon as sitting in the upper half plane, and I pin its base down, say these points are 0 and 1, and I call the tip of the heptagon tau 1. Maybe it's I in the upper half plane. Now what I'm going to do is construct another Riemann surface of genus 3 for every other point in the upper half plane. And the construction is very simple. There is a unique real linear map of the whole complex plane to itself. That's the identity on the real axis. And that moves tau 1 to tau 2 for any other point in the upper half plane. So this map, which is not complex linear, changes the angles, it changes the shape of the heptagon, but it keeps parallel edges parallel. And so in the target, I can still glue up opposite sides to get a new Riemann surface of genus 3. And so I say f of tau is the polygon defined by tau, like this one is defined by tau 2, modulo the obvious gluings, and that is my Riemann surface in genus 3 determined by that point in the upper half plane. Okay, so that's a map of the upper half plane into the moduli space of Riemann surfaces of genus 3. Next, let me give you an example of a miracle. A miracle is where that map has a huge stabilizer, and in fact its image is just an algebraic curve in F3. It's the same example. So it turns out that that example, amazingly, is stabilized by the 2-7 infinity triangle group. So it factors through a quotient of the hyperbolic plane. Moreover, the quotient is not just any old Riemann surface that we can't understand. It's one where we know very explicitly how it's uniformized, what this Fuchsian group is, and we also know extrinsically what this curve is. This is what's traditionally called the Klein quartic. It's a very symmetric curve of itself of genus 3. So this is kind of the spirit of these Teichmuller curves. When you find one, you get a complete package. You get a description of a family of curves in moduli space, but you also get a description of the curve itself, which sweeps out that family. And everything is just in terms of polygons. It couldn't be simpler. Okay, now, what does this have to do with billiards? Who said anything about billiards? Well, in fact, this is closely connected to some even more elementary problems about billiards and polygons. So let me give you an example of what I mean by billiards and polygons. So here is a polygon. I quickly drew this because it's the same as the shape of the nose of the pumpkin on the counter out here. And in this polygon, so these are all 90-degree angles here, we start a particle moving at some point and let it bounce off the walls. In fact, it's moving here at exactly a 45-degree angle. It's bouncing around in this polygon. I've drawn a very long trajectory. And in fact, what you'll observe in this picture is that for some reason, whatever's happening, this trajectory never enters the two corners of the billiard table. But also, and this is not quite clear from the picture, but it's true, this trajectory never closes up. So it goes on forever in both directions. So it's an example of some dynamics in this billiard table, which is neither periodic nor uniformly distributed. It's some sort of intermediate dynamics. And I learned from Arnold that if you want to define something, you should first give an example of something that isn't it. So I want to define the notion of optimal dynamics. Optimal dynamics means every trajectory is periodic or uniformly distributed. This is non-optimal dynamics. Okay, that's what you avoid when you have a billiard table with optimal dynamics. By the way, billiards in a square or a rectangle is optimal. In a square, the trajectory either has rational slope, in which case it's periodic, or irrational, in which case it stands in uniformly distributed. But that's special to the square. What happens with more complicated polygons? Well, let me now give you the classical connection between billiards and Teichmuller curves. Namely, if we wish to analyze billiards in this L-shaped table, what we can do is replace this path, which changes by reflection each time it hits a side, with a path that simply goes through to a copy of a new table when it hits an edge. So rather than considering reflection taking place inside this one fixed billiard table, I put a reflected copy of the billiard table and I allow the ball to go straight. Then when it hits another edge, I put another reflected copy of the billiard table. And then when it goes to this third edge, I could put yet another copy, but it turns out that copy would be the same as this copy. So when you hit this edge, what the ball does is it magically reappears over here. And the virtue of this picture is that the ball is always going in the in the same direction, it has constant slope. And we're just studying straight line flow, no longer in this L-shaped billiard table, but in this more complicated polygon with some identifications on its edges. Well, that more complicated polygon folds up to give a Riemann surface, and the metric is recorded by a holomorphic 1 form on that surface, which just comes from the form dz in this picture. And these four corners here are all glued together to a single point. So there's a lot of excess angle at the image of that corner. Elsewhere on the surface, there's a flat metric. This is what's called a flat surface, this Riemann surface with this additional structure. And from this flat surface, we generate a complex geodesic by changing the shape of these polygons. And we pray that that geodesic generates one of these numerical type-Miller curves, because when it does, one can prove the billiard table has optimal dynamics. Okay, so that's a quick summary of why billiard theorists are interested in these type-Miller curves, or how people who work on type-Miller curves justify what they're working on to people who only understand billiards. Okay, so what do we know? Well, the main theorem in this subject, the one that really got it going, was the proof by Veach. Veach showed that the program I just sketched actually works, and used it to prove that billiards in the regular n-gon is optimal. Every trajectory is either periodic or uniformly distributed. And I chose this based on the two eyes of the pumpkin outside. Okay, so that was a great result in the connecting the theory of billiards to the theory of these type of curves. Now, I want to give you a hint of how this theory looked in the 20th century. So in the 20th century, there weren't so many examples of type-Miller curves or these optimal billiards known. But one thing that was known, it was discovered by several people, sometimes using computer searches, sometimes using other methods, was that in addition to the regular n-gons, there are three special triangles that also have optimal billiards. And I've described these triangles by indicating the proportion of the total angle that's allocated to each vertex. So the sums of these numbers should be 1 in each case. So it's pi divided by 3, pi divided by 12, etc. And it was shown that each of these three triangles has optimal billiards. And I should say, we still don't know which triangles have optimal billiards. For the acute and right angle triangles, the theory is complete, but for obtuse triangles, even there, a classification is an open problem. But one thing we now know is that we should have discovered this earlier. It would have been great if it would have been discovered at Chicago. I mean, at Toronto. Chicago also. And the reason is that, as Chris Leininger showed, these triangles can be discovered a la Coxeter. That is, associated to each one of these triangles is one of the three exceptional spherical Coxeter diagrams, E6, E7, and E8. And more precisely, these Coxeter diagrams can be thought of as describing certain systems of simple closed curves, two of them on surfaces of genus 3, the third on a surface of genus 4. And from these systems of simple curves, one can build a hyperbolic, a complex geodesic in moduli space. And then it's a general theorem, that's observed by Leininger, that when these diagrams are spherical, the corresponding complex geodesic, in fact, maps to a type-Miller curve. And so really, if you can see the connection between this triangle and E8, then really Coxeter's ideas lead to a very beautiful way of conceptualizing where these come from. So I want to finish by just giving you a glimpse of where we've come since the late 1980s, which was when Veach discovered that the regular n-gons have optimal dynamics. So we have the regular n-gons, we have triangles, but in the last couple of years, there's been a foray into the world of quadrilaterals. That's the next step, from 3 to 4. And there's a big difference between 3 and 4, which is that a triangle is completely specified by its angles up to similarity. But a quadrilateral has a modulus associated to it. There you can specify the lengths of the first 2 edges arbitrarily, and then while keeping the angle space. And in joint work with Alex Eskin, Roger McMullen, and Alex Wright in 2017, we uncovered a suite of 6 quadrilaterals with many beautiful properties. Here's pictures of the quadrilaterals. Of course, none of them are convex. And these numbers here are, again, giving the internal angles. So the internal angles here are proportional to 111 and 7. Here they're proportional to 111 and 9. So what's special about this suite? Well, first, every member of each of these 6 examples gives rise to some sort of higher dimensional analog of a type-Moore curve. It's what's called an SL2R invariant 4 manifold, sitting in not quite the moduli space of curves, but the moduli space of 1 forms. And these 4 folds have some very unusual properties that were unexpected, and the fact that they even exist shows that the theory is deeper than what might have been thought. The second thing I'd like to emphasize is that among these 6 quadrilaterals, 2 of them give 2 new infinite series of optimal billiard tables, and therefore 2 new infinite series of type-Moore curves in the moduli space of Riemann surfaces of genus 4. And so you have to choose the sides of this triangle correctly, but if you choose them, there's an infinite set of choices for the ratio of the lengths of these 2 sides, such that billiard in the corresponding quadrilateral has optimal dynamics, and similarly for this example. But I think what's really shocking about this theory is, well, it's not so much that the Star Trek symbol seems to be implicitly appearing in mathematics, but it's that a miracle which I could almost prove can't possibly happen does happen here. And I think none of us who were working on this project ever expected this miracle to happen. And what's happening again is, if I can just reduce dimensions by 1, is that we have this moduli space M4 and some sort of curve sitting in it. This is our type-Moore curve, but actually attendant to this, there's some sort of a 3-dimensional space which is ruled by type-Moore curves, and this 3-dimensional space naturally would project to some lower dimensional moduli space, and now the Riemann surfaces have to have mark points, so it's a moduli space of type MGN, and this pencil of geodesics along this curve here maps to a 1-parameter family of geodesics through a single point on a complex surface, F, contained in this bigger moduli space. So here we have the miracle of V, which was with the dimension of V equal to 1, and V totally geodesic. And then almost by serendipity, it turned out that some of those V give rise to surfaces. So the complex dimension of F is 2, and F is again totally geodesic. That means if you pick any 2 points on this surface, the type-Moore geodesic between them lies on the surface. So these maybe deserve to be called type-Moore surfaces as opposed to type-Moore curves. And for example, the universal cover of a type-Moore curve is something that's well known. It's the upper half plane. We don't really understand what the universal cover of this space is. It's almost as if there is a new type-Moore space of dimension 2 which intervenes to form the universal cover here. So all sorts of traditional problems about type-Moore space should be applied to the universal cover of this totally geodesic surface F, the type-Euler curves themselves I think of as rare jewels. I have no words to describe how precious these objects are. We only have 3 examples of them. They may be all the examples in the world, so far as we know, that they come from these 3 quadrilaterals, and they give totally geodesic surfaces in the moduli space M13. Those are Riemann surfaces of genus 1 with 3 mark points, 4 mark points, and surfaces of genus 2 with 1 mark point. And in fact, there's a little algebraic geometry story that allows one to explicitly describe in sort of classical terms what these various totally geodesic surfaces are, but which does not reveal in its own right the miracle in the fact that they're totally geodesic. So let me just conclude by saying I had the sad pleasure of the conference on memorial of, I had the sad pleasure at the conference in which Perelman did not accept the Clay Prize to give a lecture in the Institut Oceanographique in Paris. And it's a beautiful place. And this is just a scene from the lecture theater. And I think this scene is an appropriate place to end the discussion of dynamics on moduli states, because I feel that, like these oceanographic explorers, we are still in the age of discovery.
Thank you so much for this beautiful talk. I'm sure there are questions.
When in mass physics we are talking about equidistribution of billiards, we usually looking for equidistribution in phase space, not in. In square, definitely it's not the case, but we have a polygonal example.
In the polygonal examples, as I showed, when you unfold these to give flows on Riemann surfaces, the trajectories remain parallel to each other as they evolve. Yes. So you do not have equidistribution in phase space. You have, in almost every direction, however, you have equidistribution on the surface. However, there's a beautiful result, which is due to 2 members of the audience, plus Smiley, Kirchhoff, Maser, and Smiley, which is that there exists triangles where now the angles are not rational multiples of pi, so you can get some mixing going on in phase space, and where the dynamics of the billiard flow is ergodic, not just on downstairs, but on the phase space itself. Is that fair to say, Steve?
Other questions?
Yes, Matt?
So, I remember 15 years ago you made a conjecture in your seminar that we now know all of the series of type-Euler curves. I was just wondering if you would make that conjecture today.
Did I really make that conjecture? I think I said, could it be?
Oh.
So here's my current view, and this is not informed so much by mathematics, it's just my increasingly acute sociological observation. I think the examples that we know are the ones that are easily accessible by human beings. And in fact, they all, the fact that they come from quadrilaterals and triangles means they all come by starting with a Riemann surface with some very simple symmetry. It's like a cyclic cover of the projective line. And it could easily be that we just don't have the imagination to find the other ones with more intricate and more interesting constructions. And I'll come to that issue more broadly in my next talk. But I should also say there is a heuristic argument that was available 15 years ago, which explained why you shouldn't be able to find any in genus 4, more than 4. Or rather, it indicated it was unlikely there would be infinite series of type-Euler curves in genus 5 or more. And in fact, that's still, it's not a conjecture, but it would be a real breakthrough to find infinitely many primitive type-Euler curves in genus 5. Everything we know is taking place in low general.
clearly a great beginning to the Talks of the Lecture series. Before we thank Isabella again for this inaugural talk, just to say that you're all most warmly invited to the reception of the atrium here to continue the discussion and ask further questions. Thank you again. Thank you.
Yeah, I hope it's okay to have someone.
Fling it. Anybody?
You don't have Oh, so here's something that's. So